we're off to the races. So this chapter is called Using Entropy. So in the last chapter, we talked about basically it's the fundamentals of using entropy. And how we did it was we did the second law, right, and all of the corollaries and all of the ways it's applied. But in this chapter, we're going to be using entropy for processes such as like turbines and compressors and things like that. That is the basis for this chapter, is using the knowledge we gained from the last chapter to understand irreversibilities in this one. So this is more of a numeric chapter. The previous chapter was very, conceptual based, right? This one is numeric. So we are going to be finding numbers here using the tables because if you guys recall, I know it's been a while since we've really used the tables, but if you recall, there is an entropy value right here in the tables, and you find them using the exact same way you did before. But we'll get to that in just a minute. So chapter 6, using entropy. So here we go. It says an entropy, a system property. So it says the word energy is so much a part of the language that you were undoubtedly familiar with the term before encountering it in early science courses. This familiarity probably facilitated the study of energy in these courses and in the current course in engineering thermodynamics. In the present chapter, you will see that the analysis of systems from a second law perspective is effectively accomplished in terms of the property entropy. So this is why we talked about the second law before this chapter, or else it really wouldn't make sense, right? So it says energy and entropy are both abstract concepts. However, unlike energy, the word entropy is seldom heard in everyday conversation. Yeah, we don't really hear that much. And you may never have dealt with it quantitatively before. Energy and entropy play important roles in the remaining chapters of the book. That is definitely true. Entropy, just to let you know how I don't want to scare you, but how serious this chapter is for the rest of the book. Entropy, there is not a single question from chapters 8, 9, and 10 where you will not have to find entropy. Just to let you know, not that you won't have to find entropy, but that you will have to be using properties of entropy to understand it. So entropy is used for all of Thermo 2, except for the last chapter, which is combustion. So it says, defining entropy change. So it says a quantity is a property if and only if its change in value between two states is independent of process. It says this aspect of property concept is used in the present section together with the Clausius inequality to introduce entropy change as follows. So, two cycles executed by a closed system are represented in figure 6.1, so that is this over here. And it says one cycle consists of an internally reversible process, that would be process A, from state 1 to state 2, followed by an internally reversible process, C, from state 2 to 1. And then it says, the other consists of an internally reversible process B from state 1 to 2, followed by the same process C from state 2 to 1 as in the first cycle. For the first cycle, equation 513, which is the Clausius inequality, takes the form of the following. So you guys remember this, right? Hopefully. So this is the heat transfer over A of the boundary of A, right, from 1 to 2, plus the same thing from the boundary of going back the other way, 1 to 2, from C, essentially. So this is the C going this way. So we did this, and then back around. Here. And it says is equal to sigma cycle, which is equal to 0, because if you guys recall, for a internally reversible process, sigma cycle is 0. And the reason why it's 0, because our process was 100%, it created no entropy, right? We gained no entropy because if you recall, I mentioned that sigma cycle then turns into, it's just entropy created or entropy gained, which is what sigma basically means in this chapter. In the previous chapter, they like to use sigma cycle, but in this chapter, it's just going to be entropy gained, which is the term sigma. And then it says for the second cycle, equation 513 takes the form of the exact same thing, right? Except instead they used this. They went on B's path, 1 to 2, and then down to 2 to 1. And it says is equal to sigma cycle is equal to 0. It says in writing, Equation 6.1. The term sigma cycle has been set to 0 since the cycles are composed of internally reversible processes. Like I said, if they're internally reversible, sigma cycle will be 0. It says when 6.1b is subtracted from equation 6.1a, what you get is the following. You get this. And what that means is that that it says this shows that the integral of dq dt is the same, or dq over t is the same for both processes. Since a and b are arbitrary, it follows that the integral of dq over t has the same value for any internally reversible process between the two states. In other words, the value of the integral depends on the end states only. It can be concluded, therefore, that the integral represents the change in some property of the system. Selecting the symbol S to denote this property, which is called entropy, the change in entropy is given by this. Right here. So basically what that said is that because we found that this isn't a path-dependent equation, right? And what that means is it doesn't matter what path they took to get there. All it matters is the beginning state and the end state, right? That's all we care about. That's the only effect that it has, is the beginning state and the end state. And so, since we figured that, that means that this is just simply just a measure. It's a measure of something changing, right? Since we know it only matters about the end and beginning, it's a measure of something changing. And what they did was they made it entropy, which is this right here, S, is entropy. And it says where the subscript int reversible is an added reminder that the integration is carried out for any internally reversible process linking the two states. On a differential basis, the defining equation for entropy change takes the form of ds is equal to that same thing, dq over t. So essentially we just remove the integral, right? And then it says entropy is an extensive property. And then it says the SI unit for entropy is joules per Kelvin. However, in this book, it is convenient to work in terms of kilojoules per Kelvin. And then it says a commonly employed English unit for entropy is BTUs per Rankine. Units in SI for specific entropy are kilojoules per kilogram Kelvin. So that is what you will see for entropy in our table. Is because remember, all of these are represented in terms of mass, right? There is kilograms on all of these. And so entropy, which is this one right here, is kilojoules per kilogram Kelvin, is our unit. And then it says, so the English units are BTUs per pound Rankine. And then it says commonly used English units for specific entropy are BTUs per pound Rankine and BTUs per pound mole Rankine. So it's the same thing for the SI as well, kilojoules per kilogram Kelvin, or kilojoules per kilomole Kelvin. And it said, it should be clear that entropy is defined and evaluated in terms of particular expression, for which no accompanying physical picture is given. We encountered this previously with the property enthalpy. Enthalpy is introduced without physical motivation in section 3.61. Then in chapter 4, we learned how enthalpy is used for the thermodynamic analysis of control volumes. As for the case of enthalpy, to gain an appreciation for entropy, you need to understand how it is used and what it is used for. This is the aim for the rest of the chapter, is to figure out how, right? So, it says evaluating entropy. Since entropy is a property, the change in the entropy of a system in going from one state to another is the same for all processes, both internally, reversible, irreversible between these two states. Thus, equation 6.2, which was the one up here, 6.2a and 6.2b, allows the determination of the change in entropy, and once it has been evaluated, this is the magnitude of the entropy change for all processes of the system between the two states. The defining equation for entropy change, 6.2a, serves as the basis for evaluating entropy relative to a reference value at a reference state. Both the reference value and the reference state can be selected arbitrarily. The value of the entropy at any state, y, relative to the value at the reference state is obtained from the following. So all they did was essentially this is the exact same equation as before. As S2 minus S1 is equal to this right here, but they just moved S1 over. So S2 would be equal to the entropy at the first state plus this process, right? Q over T, right? Or dq over T. And that makes sense, right? So if we have some entropy at the first state, something had to have happened if we went up in entropy. We had to have gained something, right? Although this is an internally reversible process, so we didn't gain the entropy. But essentially, something had to have happened for S2 to not be the same as S1, right? Something had to have happened. So we have gained, through the process, we have gained entropy. And then it says, where Sx is the reference value for entropy at the specified reference state. The use of entropy values determined relative to an arbitrary reference state is satisfactory as long as they are used in calculations involving entropy differences, for then the reference value cancels. This approach suffices for applications where composition remains constant. When chemical reactions occur, it is necessary to work in terms of absolute values of entropy determined using the third law of thermodynamics, chapter 13, which is this. Chapter 13 is combustion, which is the last chapter of Thermo 2. Let me see. This is probably helpful. So it says entropy and probability. So it says the presentation of engineering thermodynamics provided in this book takes a macroscopic view, as it deals mainly with the gross or overall behavior of matter. The macroscopic concepts of engineering thermodynamics introduced thus far, including energy and entropy, rest on operational definitions whose validity is shown directly or indirectly through experimentation. Still, insights concerning energy and entropy can result from considering the microstructure of matter. This brings in the use of probability and the notion of disorder. Further discussion of entropy, probability, and disorder is provided in section 6.82. So what I said the other time was essentially this right here is the word, the key word, is that entropy is essentially just the measure of disorder, right? And so that is our working definition of it. But obviously when you start to get at a macroscopic level, or a microscopic level, so like how we in this class will deal with things is like here, like this is a cycle, you know what I mean? You know, this is a cycle, right? This is what we care about. But in reality, if you take a little close up here, and we're like, here's the little atoms, right? And here's how we get the thermodynamics, like how the properties interact. That is the microscopic view, but we don't really care about that. Not right now, at least. But you can, Thermo 3, which is Thermo 500, has a section on microscopic thermodynamics. And this book is the same book that uses it. I can't remember what chapter that's in. I think it's like 11 or 12 where you do microscopic thermo. But we don't even really care about that for right now. Our working definition is fine for that. It is the notion of disorder. That is it. So then section 6.2, it says, in chapter 3, we introduced means for retrieving property data, including tables, graphs, equations, and the software available. The emphasis here, or there, is on evaluating the properties P, V, T, U, and H. Pardon me. Required for the application of the conservation of mass and energy principles. For application of the second law, entropy values are usually required. In this section, means for receiving entropy data for water and several refrigerants are considered. So we know how to do this, but we are going to do, just to refresh this, I'll do them right here. Okay? So, not a big deal. We'll start here. So it says, in the superheated regions of the tables for water and the refrigerant, specific entropy is tabulated along with V, U, and H. It says, consider 2 states of water. At one state, the pressure is 3 megapascals and the temperature is 500 C. So I'm going to put this over here. So P equals 3 MPa, just so I can remember it. 500 C. Okay. And then it says at state 2, the pressure is 0.3. So let's just we'll do 1. P2, T2, 0.3 MPa. And the specific entry is the same as state 1. Ah, okay. Cool. Got it. So it says, what we need to do here is, it says the object is determine the temperature at state 2. So that's what we're trying to find is T2. And I used a highlighter. All right. So T2 state. So the first idea is to go look this up in the table. So we must go to 3 megapascals. Let's go to the pressure table. I'm pretty sure 3 megapascals is what, 30? I think it's 30 bar. I think it's right here. I'm gonna make sure of that though before I do this. 3 MPa 2 bar. Pretty sure it's 30. I was right. So 30 bar, which if you remember, we go down the table here. You go look at 30 bar, and you look at this temperature. Our temperature at state 1 is it's actually double this, right? Over double. So that means that we are superheated, which is the question as it suggested. I know the question said it was superheated, but always check. It's a good habit. So let's go look at 30 bar. 30 bar is right here, which is 3 megapascals. And then you go down, slide across to the states here. Now, how this works is, so this is specific volume, this is internal energy, this one is enthalpy, and the last one is entropy, right here. So this is entropy. So we need to write that down, and I will do so right now. So S1 is equal to S2, which is equal to 7.238. Now, really fast, this is something that's going to happen a lot in these later chapters and in Thermo 2. Sorry, didn't get much sleep last night. You are going to have to grab an entropy value, just like this, and use this to go from one state to the next. Because in how you solve cycles, you make the assumption that S1 is equal to S2. And the reason why you make that assumption is this right here, if you guys are following along, is that S1 is equal to S2 means that the process that we went to for like the turbine is perfect, right? It's an isentropic turbine, which means no entropy gained. And so if you say S1 is equal to S2, you know S1, you can find S2, and then from there you work with the efficiency and actually get a real number for S2S, or this should be S2S. But that'll be something we get to later. Don't focus on that for now. What you should focus on is that it's this sort of pattern is where S1 is equal to another S, and then you use this S that you found to find something about the last state. It's the same thing we did with specific volume in the first chapter, right? Where you found something about so you found everything about the first state. With temperature, pressure, you found specific volume, and then the specific volume was the same as it was in state 2, right? If you remember these questions where it was like it's a rigid tank. But only for us, you will use S1 is equal to S2 when instead of a rigid tank, it'll be something like a compressor, a turbine, a pump, things like that. Instead of rigid tanks, S1 equals S2 will be for those types of processes. So now that we have this written down, we now go back. So when we go back here, we need to find where does this end up, right? So we know that the pressure dropped here. As you guys can see, our pressure, it went down by a lot. We are now at 0.3 megapascals instead of 3. So what we need to do is we need to find where we're at. So how you compare it is you go to 0.3 megapascals and you look and see if this value of entropy fits in between the range of values acceptable, right? Which is over here. So I'm going to go ahead and remove these arrows and I'll talk through it. So we need 0.3 megapascals, right? So 0.3 megapascals, only assumingly that is 3, right? 3 bar. I'm making sure just in case I mess that up. Yeah, it's 3. So we go to 3, which is bar here at our pressure 2, and we slide across. And you see that the range of acceptable values here is what? Is our number greater than or less than? Is it inside of this range? How about answer that?
Ours is greater than that.
It is greater than. So that means it is greater than this number. And if you recall, this number represents saturated vapor. So if we look on the chart here, you know, your diagram, this right here is saturated vapor. So this is a quality of 1. This is a quality of 0. We are beyond this. So this is where those TS diagrams come into play, is that right here would be an entropy of 6.9919. But ours is higher than that. We are further along. We're up here, right? Which means what?
Superheated vapor.
We are still a superheated vapor, correct. We are past the line, which means that we are a superheated vapor still. And this is why it's important to check, is that because that could have just have easily been down here. And, a lot of people like to assume, they go, oh, well, our pressure dropped, right? And we kept the same entropy, so everyone thinks, oh, well, we're in here. We're in the saturated region. Sometimes it works out like that. Sometimes it does not. It depends on the thermodynamic cycle you are undergoing. Sometimes it ends up superheated. Sometimes it ends up saturated. So you do have to be careful. So that means we now go to the next part, which is back to the superheat tables. We go. And we go look at 3 bar, and we slide across. So we're looking for 7.2338. So 7.238. So that's 7.12. This right here is 7.3. So we are somewhere in between here, right? Is that fair to say? Somewhere in between. So you would say that our temperature is what, around 180? I'm just going to say 180. We'll see what they say, but I'm going to say it's in between these two numbers, right? Because our number, 7.23, fits in between here somewhere, because that's 7.3 and that's 7.1. So it's in here somewhere. And it's on the 0.3 megapascals chart. So I'm actually going to see what their answer was. They say that if you interpolate, you get 183, which is believable to me, right? If you guys use the logic that I just used at the table, you would see that this value is something that you would expect to get, right? So, all worked out for us there. And that is the right answer, in my opinion. And I found my other calculator, by the way, so now I can interpolate. I have it. So I could have done that, but why do it? And now we're moving on to saturation data. So that would be inside the curve or on the saturated tables. So you guys, I don't know how much more we need to spend on this, because specifically you use the exact same equation as you used before, right? So like x would be equal to S1 minus SF over SG minus SF. And that turns into the exact same equation where it would be S1 is equal to SF plus X times SG minus SF. It's the exact same equation you used before with enthalpy and internal energy and specific volume, except it's with entropy. So it's not really that difficult as long as you know equality, which you might have to find. But the case in this time, though, guys, is that if you need to, so this is where things can get different, right? Is because before, in processes such as the rigid tank, right, or whatever, in processes such as that, you would use specific volume, right? A lot of times specific volume would be what you would use here. You would go, V1 is equal to VF, and you would write all that in, and you would find a quality using volume. Now think of it as the opposite way. We're going to be using entropy to find quality, and then use our quality to find internal energy, or for us, it'll probably be enthalpy. So before, how we did this in the beginning chapters, it went volume to quality to U, or H, right? This chapter, it's going to go S to X to U or H. That's how we're going to do things in this chapter. And honestly, this process right here will be how you do things for the saturated region for the rest of the for the rest of this class and for the rest of Thermo 2. It's this exact same process. When something falls in the saturated region, you will do this. Entropy to find quality, to find internal energy or enthalpy. Because if there's one thing we know You are finished with the question when you have found every state's enthalpy value and every state's entropy value. You've finished the question, because most questions ask you for the work or the heat transfer, and those are represented by H's and U's, right? So you know you're done when you figure that out. So we can talk a little bit about it, but I don't think we really need to. I'll just go through it really fast. So it says that, refrigerant 134A, temperature is 0, and the specific internal energy is 138. I'm actually going to have to write that down. I won't write down the rest of it, though, because I'll forget that. So it says refrigerant 134A, so I'm going to go find 134A. That should be the next table, though, if I'm right. Nope, 22, then 134. Yep, here it is. So this is saturated 134A. So what they have given us is the following. They've given us a temperature of 0, which is this, right? 0 degrees. And they've given us a specific internal enthalpy, or internal energy, of 138.43. So you slide across and you look at the internal energy category. Is our value in between these two numbers? Answer is yes. This is the saturated liquid value. This is the saturated vapor. Our value is 138. It's between these two. So that means you just find, now what you do is you find your quality using that number. So it will be X is equal to 138.43 minus 49 over, what is this number? 227.06 minus 49.79. And the answer, as they find right here, is 0.5. Perfect on the dot, half. So they get 0.5. So I'll just go ahead and get rid of this then. So they find it to be 0.5, just like we used to do. Finding quality, you get 0.5. And then they find entropy, because the purpose of this was to find entropy. So now that you know quality, you plug the entropy equation in. You would say S, or S1, or whatever the state is. Whatever the state is, you would just say S1 is equal to SF plus X1 times SG minus SF. And where you'd get these values, same place we got the ones before. You would go up here and you would take this SG value at 0, which is 0.919. So I'm actually going to do that. So it'll be 0.197 minus, or plus, 0.5 times 0.919 minus 0.197. And what they get is the answer is the following. They get 0.558. So this right here is the process. It's the exact same as the ones we've been using before, except that specific volume kind of gets left by the wayside. We don't use it much anymore, except for closed rigid tank questions and piston cylinders. So essentially think of it this way. For like piston cylinders, for closed systems, I'll just make this a little more easy. For closed systems, specific volume is still used. For open system, you do not use specific volume again, except there's one case, which is pumps. But that's it. And we don't really need to talk about that yet, but pumps you will use it, but that's the only piece. And then liquid data, which is the last way. Very simple. You do the exact same thing we did before. You look up, if this is like subcooled liquid, you look up enthalpy or your entropy at the temperature. So you take the SF value at the temperature given. So I will go and do that really fast as well. This one won't take long though. So it says, suppose the value of a specific entropy is required for water at 25 bar 200 C. So specific entropy, so they obtained it from the table directly. I'm going to go look it up at this. So 25 bar 200 C. So first off, we're gonna go make sure that, is this for water? Yeah, it is for water. I'm gonna go make sure that this is actually in the subcooled region, because like I said, you always make sure. So it says 25 bar, 200 C. So let's go look at 25 bar. 25 bar, 200 C. So we are below this line. Just to tell you right here, we are below that temperature. So that means we are subcooled. That is a check. And then what we do is, now that we know it's there, you do not, I repeat, you do not grab any of these values for saturated liquid. Do not, because they are wrong. You then go look it up at, its temperature in the temperature table. So let's move over to the temperature table. So now that we know it's 200 and it's subcooled, you go look up over here. And you slide across and you pick these values up. So this right here is saturated liquid. This right here is saturated liquid. So that'll be that. This right here is saturated liquid, and this one is as well. So this is for volume, internal energy, enthalpy, this is entropy is the last one. So they wanted us to find the entropy of the last one, and it says S is equal to 2.3309, which, as you see, is the one I circled here. 2.3309, because that is the saturated liquid value of entropy looked up at the temperature, not the pressure. We approximated it. And just to show you that there isn't much of a difference, they actually went and looked it up in the compressed liquid tables, and this is what they get in comparison to that. So it's almost the same value. So, and it's not enough for us to really care. And we're not going to do the computer retrieval one, so I'm not really worried about that. Okay. And then there's one more thing, and then I'll let you guys go for today. Let me see if this is it. Enthalpy, entropy, temperature, entropy. Okay, so this is the one right here. I don't know if those are all that useful, honestly. That section's not that great, but we'll go over it, I guess, really fast. So it says, the use of property diagrams as an adjunct to problem solving is emphasized throughout this book. When applying the second law, it is frequently helpful to locate states and plot processes on diagrams having entropy as a coordinate. Two commonly used figures have entropy as one of the coordinates are the temperature enthalpy diagram and the enthalpy entropy diagram. So really fast, I have never used the enthalpy entropy diagram. I think the only time I've ever, I don't even know if I've ever used, actually I don't think I have. I don't think I've ever used it. I think this one right here though, TS diagrams as I've called them, so this is TS diagrams, so temperature enthalpy diagrams. This is the most commonly used one. You will use this on like every question. So that is something I'd pay attention to. So it says the main features of a temperature enthalpy entropy diagram are shown in figure 6.2. For detailed figures for water in SI and English units, see figures A7. Observe that the lines of constant enthalpy are shown on these figures. Also note that in the superheated region, constant specific volume lines have a steeper slope than constant pressure lines. Lines of constant quality are shown in the two-phase liquid vapor region. On some figures, lines of constant quality are marked percent moisture lines. The percent moisture is defined as the ratio of mass of liquid to the total mass. In the superheated region of the TS diagram, constant specific enthalpy lines become nearly horizontal as pressure is reduced. These superheated vapor lines states are shown as the shaded area on 6.2. Okay, so all of that things, don't worry about that. I just want you to know this is the TS diagram. So here, I'm actually going to, before we go, I'm going to pull up a paint. Oh, come on. Paint 3D. And I'm going to do really fast just a TS diagram of very simple states. So I'm just going to grab some states here. I'm going to say for water, ooh, big numbers. I'm going to say for the first one, P1 is equal to 10 bar, right? Let's just say 10 bar. And I'm going to say, I don't know, give me a temperature. Anybody? Just give me a temperature. And we'll find out where it's at. I need a volunteer from the audience. 300C. Gotcha. 300C. Now let's do P2. Let's do 0.1 bar, which is, and then we'll do what? We'll do 70 degrees. So T2, we'll do 70. C. That'd probably be superheated as well, maybe. I don't know. And then let's do the last one. Let's make sure this one is let's make sure this one is actually what we need it to be, which is subcool. So P3 is equal to let's do 1 bar, and T3 is equal to 90 C. So these are our 3. And I'm going to go ahead and try and chart these off. Although I don't think we're going to get one saturated because I didn't really pick that one very well. But I could have done it with this one. So what you do here is, let's grab, so I'm going to draw our TS diagram. And we're going to do so this will be temperature, and this will be entropy. And these are extremely helpful, I promise you. I think getting into these to learn how to draw them would be extremely helpful for everybody. So now let's draw this weird region in the middle here that I'm not very good at doing. Something like that. Sure, weird region in the middle. So this is what we're working with right now. So now what we do is we go and look up each one of these and figure out where they lie. So I'm going to go do that. So we have first one for 10 bar, 300 degrees C. And we want water. So 10 bar here. And we are over the saturated temperature, right? 10 bar, and we have 300. We are way over. So that means we go to the superheated region, and we find this. So we go 10 bar, 300 degrees C, classic Tanner. You picked one that's not on the table. Thank you. And what we do is we look it up here, and you find our value where we're at. So you made it difficult. So our value is in between these two, right? But the important part is that we know where it's located. These diagrams are not meant to be perfect. And what I mean by that is it's not meant to be like perfect in all ways to where you always like where these are touch tight with each other. And I'll show you what I mean is that essentially, so this is 10 bar, 1 bar. So let's do this. Temperature is 300 C, right? So we have so I'm going to draw our lines of constant pressure. So this will be a line of constant pressure. So it means everything on this line is the same pressure, okay? That's what it means. So lines of constant pressure. I used to have a friend that during this class, she would like to remember how these looked, because whenever it's pressure, temperature lines go the opposite. So they go like this. So she would like hold her hands out or like her arms and do like the squiggly with her arms to tell which way it would go. But yes, it was effective for sure. So what you do is you go up this line of constant pressure, and so this pressure, you mark it as this. So this is how you would do an actual one. You would go P1 is equal to 10 bar, right? So this pressure is equal to 10 bar, and then you would go, well, we aren't inside of here because we're superheated, so you would just go up here and draw it anywhere. Really anywhere. It doesn't really matter as long as you label it properly. So we have one up here, and then what you do is, this would be what you would do on your paper, is you would draw like a little line right here. I don't know if that's level or not, and then you would say T1 is equal to 300, right? You do something like that. To show that right here, we are on this line of constant pressure. You have 10 bar. Over here, straight across is 300. And then you do the next one, right? So we have P2 is 0.1 bar. Like I said, the scaling of it is however you want it to be, because like for example, you can draw this and say this is the number, this is the entropy value, just as long as it makes sense, right? You know, for example, if the temperature for the next one was, let's say it was 299, and you had it down here, it really doesn't make sense like that, right? Just as long as the scaling of it makes sense and it looks okay, it'll be pretty effective for you. So let's look at the next one. So 0.1 bar. So once again, I have to go make sure that it's in its right region. So 0.1 bar, which is right here. 0.1 bar, 70 degrees C, so we are over this because we are bad at picking examples. So 0.1 bar, 70 degrees C, so we are back in the superheated region. And this one will definitely be between values, I'm going to guess. And actually, they don't even have 0.1 bar as a as a value. So this one would be even more painful because we'd actually have to go and find values in here. So I'm just going to, we don't need the values though right now. We're just drawing pictures. But real quick, I'm going to draw it how you should. So since you know this is 0.1 bar and this is 10 bar, this should be way lower. So it should be down here, right? And like that. And then like this, right? And since we know it's superheated, you once again go and draw it over here somewhere. Once again, doesn't really matter where on here, just as long as it's in the right region. So right there, and then you draw your line over here. And I'm just going to quickly do it. And just say that's where that one is. 70. And then the last one here is very clearly subcooled because pressure, or so 1 bar, which is what atmospheric temperature is, or atmospheric pressure is, it's the boiling point is like 99, so we are below that, but we can prove that anyway. That's why I picked it. But we'll prove it anyway. So at 1 bar, 99.63 is the boiling point, so we are not there yet, the saturation temperature. So we go back here. We know we are subcooled, so we draw this. But remember, our pressure is a little higher this time. So since we are trying to draw lines of constant pressure, our pressure might look like this for this the last one, right? Because it has to be higher than the one before. And if you, so essentially these are like a bunch of infinite, like you can infinitely cut this, right, into a bunch of different things, like going up and making the pattern, right? You could continuously add lines of constant pressure all the way up, and that's how these look. But you want the scaling to be right. So here, this is, I'll draw this one. So this is P3 is equal to 1 bar. And then I'll draw the last one because I forgot to add that. P2 is equal to 0.1 bar. So then you go draw your air where it's at. And since we know we are subcooled, you just have to be below here. So right here will be fine. And then slide across and you draw T2 or T3 will be equal to 90. So I actually recommend doing this for cycles because I think cycles, this is super helpful to see state points, because how cycles end up looking is the following. Like it'll look stuff like this. It'll be, you know, you start here, you go down, go across, you go up, and you come back around. This is essentially what it looks like. And so it'll be a state here, one here, and one here, right? This right here is a basic Rankine cycle, but they become far more complex than this. You'll have, 10 points in the cycle, 8 points in the cycle, stuff like that. A bunch of intermittent things that you have to keep track of. And on this, there might be 3 pressures in your cycle. There might be a top pressure, a bottom pressure, and then there might be one here in the middle. So this will come down here, then come down to here, and then there's a bunch of states in between. So using these is very effective, and I cannot recommend it enough. And if you can master using these these big pictures, the TS diagrams, you will never be lost on where a state point is supposed to go. You will always know where you're at. And that's why I cannot recommend it enough, is because if you can figure out that, even if you aren't quite sure what to do, like you're like, oh man, like I have a temperature and I have this, I don't even know where I'm at. If you draw it, if you like go and look at a value on the table and you draw where that value is, it'll give you clues as to where you are located as like superheated, saturated, or subcooled, and then from there you can start thinking about, oh well, how do I solve these states, right? What do I need? And so that's why it's really useful. And besides that, I'm going to go ahead and stop.